right?
Okay. So a very good afternoon to all. So today, basically, I just want to sort of like kickstart a little bit on the project of quantum error corrections. Uh, Basically, I'm not the expert in this area, but I'm trying to learn quantum error corrections as well as a few other things. So I just think that we should sort of like compile like our journey so that in the end it will become sort of like a set of perhaps lecture notes or something like that. So before we go into quantum error corrections, I think we always heard about NICs, and from the wording by itself, which is noisy intermediate scale quantum, we can sort of like guess what is NICs, but I just want to read Preskill's paper on NICs and see what is his opinion on this. So be reminded that whatever mentioned in the slide, I basically take it from the paper, and the paper is in 2018. So one thing that I think we should take note of is because now it's 2023, so perhaps because we are also not doing experiments, so we don't actually know how far we have progressed from 2018. So I think we should also take note of this. So basically, this paper is written by Preskill when I think he was given a chance to sort of like give a discussion on the current state quantum computing technologies, and he's trying to communicate with scientists and non-scientists such as entrepreneurs and investors. So I think in a way he's trying to maintain the hype so that like we don't overhype quantum computers. So why do I think that we need to properly sort of like understand NICs is because it kind of inform us what we are actually working on. Like for instance, later on I will just briefly mention about Sherlock circuits and so on. So why do we need that? And the current state of art, do we still need that kind of thing or not? So I think this is quite important for us to actually understand a little bit. So the greatest barrier of quantum computing technology is because basically we are fighting between two sides. So we know that if we want to properly uh, maintain the qubits and so that it does not decohere to environment, we actually need to isolate the qubits from the environment. So the better we do the job, the better we can store the information. But at the same time, when we also want to control the qubits and measure the qubits. So in this sense, we also want the qubit to strongly interact with the environment as well. So which is why this is kind of like a tug of war. So we kind of still need to maintain a balance between these two. So that's the current barrier according to like 2018. So the term noisy as defined by Preskill basically means we don't have perfect control of qubits. So in his paper, he basically mentioned that for two qubit gates, the error rate is around 0.1% at that time. So whereas the intermediate scale over here means 50 to hundreds of qubits, so it can be up to a few hundreds. But why do we need to set this scale? Because at that time, so the classical supercomputers cannot actually simulate quantum computers when it is beyond 50 qubits. So then, in his opinion, so NICs refers to quantum computers with some very noisy gates, and they are not protected by quantum error corrections. So why does he think that NICs does not have quantum error correction? Is because if you want to protect a qubit, basically you will need a lot of physical qubits to encode that single qubit into just to encode that single qubit. So meaning that when you try to perform quantum error correction, basically you will need a lot of qubits, and it is beyond this intermediate scale at the moment. So which is why he did not refer to any type of quantum error corrections when he refers to NICs. So over here, I also mentioned that if you want to run a proper algorithm that involves thousands of protected qubits, which is encoded, you will need millions of physical qubits. So then, what are the problems that we can study in NICs? So the first one is because we don't have perfect gates, right? So we want to minimize the circuit depths as much as possible. So which comes the term of shallow circuits. So then we want to look at what we can do with all these shallow circuits. So in 2017, I think Bravi and Gossett and Kronig, basically they show some quantum advantage even using shallow circuits. There are a few follow-up papers, but I didn't cite here. But this is the first paper. And then, of course, like the current algorithms that we have, besides the variational algorithms and so on, like the Deutsch-Schulze algorithm and other algorithms, most of them, when we try to prove quantum supremacy, meaning that quantum computers actually can uh, solve the problem faster than classical computers, they are not actually useful to us. They are just a proof of concepts that quantum computers can do better than classical computers. So then, in this next era, he also consider what kind of problems that are difficult to solve classically, but we can use next computers, and the solution is actually useful to us. So, and then the third one is the so-called NIST algorithms, meaning that we don't rely on putting everything into quantum computers, but instead we are doing some hybrid quantum and classical algorithms. So how does it work is that you provide an ansatz, and then you run your quantum circuits once, and then you measure the outcome. You use classical computers to optimize your results, and then you input back to your quantum computers, and then you run the results, run the simulations again, and so on. And then another part is the noise resilient algorithms, basically. And in a paper by Neil Laflamme and Surek, which is in 1997, they basically kind of show that it is possible to still have quantum computers when your error rate is below a threshold value. So this is directly kind of generalized from classical computations. And the last part is somewhat coming from what I learned during Italy. So basically, for because we need to make measurement at the end, right? So the kind of measurements that we theorize is basically POVMs, and let's say for example you have 3 qubits, and if you perform POVM, we expect the measurements can be separated by tensor products. But there are some local errors called measurement crosstalk errors that basically makes your measurement uh, not equal to the tensor product of the individual measurements. So this is what is called the measurement crosstalk errors, and it is discussed quite recently. And this kind of errors you cannot correct it by quantum error corrections. So what you can do is instead you try to provide a better measurement schemes. So yeah, but still there is this concept of fault tolerant quantum computing is actually also coming from this idea of thresholds. So meaning that if we can somewhat maintain a certain threshold of errors below that value, so then whenever you perform quantum computations, uh, you still get some useful results. So this is the idea of fault tolerant quantum computing, whereby you have some form of quantum error corrections, and you design your circuit such that your errors won't exponentially increase when you go through the circuit. So then we try to take some inspirations from classical computers. So how do we actually protect a classical bits from errors in classical computers? So for classical computers, the error is just a bit flip, meaning that if you have zero, you flip to one. So then it is easy because we can just copy the bit that we want to protect two more times, and then we use the majority rule. So for example, if the bit is zero, we just copy the zero state two more times, so that whenever, if let's say there is one error flipping, let's say the first bit, then you measure the second bit and the third bit together, and the majority rule wins. So meaning that if this is flip, then these two does not flip, right? So we can always correct the first one back to zero. But this also has some problems because if you have two big flips occur at the same time, then it doesn't work. So now we try to find the quantum analog of this kind of error corrections. But there are two problems because we cannot clone quantum states. And if we try to measure any of the qubits, it will collapse the quantum state by itself. So then such a gate is designed. So this is what I call the bit flip code. So meaning that, okay, so the psi over here is your qubit that you want to protect. So this is the state. So you try to add two more qubits, and then you perform these kind of gates. So over here, I just analyze step by step what this kind of gate does. So basically, at the beginning, you just have tensor product, and then after the first C naught gate, if it is zero, you do nothing. If the first one is one, then you flip the second one, which is one. And then by the third time, you do another C naught gate. So if this is one, you also flip the third qubit. So then you get something like this. So these three physical qubits protect the encoded qubit, which is zero. So that's why we put a 0L, and then this is 1L. So how does this kind of detect quantum errors? So over here, we just discuss a very simple quantum errors. So we just discuss about the prefib errors first. So this is the error correction, no, error detection basically. Uh, First, I'll just show the example first. So the example that I have is I flip the first qubit. So originally it is 000 and then 111. So I flip the first qubit to be this one to be 1, this one to be 0. So then we try to go through the whole step again. So the first step is just writing down in a tensor product form. And then the second step, you try to C naught to the what we call as the parity check qubit one, and then you C naught to the second encoder qubit to this parity check qubit as well. So what does this do is you try to compare between the first qubit and the second qubit. So you try to compare their parity, whether they are the same or not. And then you look at the other two is you try to compare the parity between the first and the third qubit. Of course, this is not the only way you can do it. You can also compare between the first and the second, and then compare with the second and the third. You can also do it that way. So here I just analyze one by one. What does it do? So on step two, you try to compare. You try to um, compare between the one and the fourth qubit. So then, if it is one, you get one. Zero, you get zero. And then you compare between the second to the fourth. So this is zero, so this doesn't change. This is one, so this changed to one. And then the fourth step is comparing the first with the last. So the first is one, so the last is one. This is zero, so this is zero. And then this is one. No, sorry. The third one is zero, so it doesn't change. The third one is one, it changed to one. So then you just measure the last two qubits, and essentially your first three qubits, it doesn't change from here, right? So then M1 over here basically measures the parity of the first two qubit, and then M2 will measure the parity of the first and the third qubit. So if you get zero, then the parity is the same, meaning that both are zero or both are one. So there's no error basically. If it is one, then the parity will be different. So then you have to sort of like repeat the same thing at least two more times. So meaning that you do the bit flip on the second qubit and then the bit flip on the third qubit, so that you kind of compute a set of truth table. Then in the end, you, according to what you measure at M1 and M2, you can know what you want to do with it. So in this case, the correction should be putting an X gate on the first qubit, and then you fix your error. So this is the bit flip code. But we also know that from the classical counterparts, so classically a bit can only be flipped, right? But for qubits, besides that it can be flipped, you can also change the phase. So that's why we also have this phase flip code. So again, we begin with the same thing. So this is the qubit that we want to protect. So now the first part is the same thing as before, but if we want to have phase flip code, then we just add Hadamard gates after this part. So what does Hadamard gate do? Hadamard gate just turns your 0 to plus, and then your 1 to minus. So basically, we already know what the first part of this circuit does. So we can just write the answer. Then you apply Hadamard gate individually. So you just get plus, 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 and minus, minus, minus. So this together is encoded into plus, and this together encoded is minus. So this is the encoded qubit. So now again, we consider the same thing. If there is a phase flip error on the first qubit, so the plus becomes minus, and then the minus becomes a plus. So you can see that the structure of the error detection is the same thing over here. So what is different basically is you just have some extra Hadamard gates. So what this does is basically it turns back your plus back to your zero as zeros and ones. So once you have 0 and 1, you see that this is basically the same problem as before. And then this part just detects your error. And then after you detect the error, you turn the first 3 qubit back to the plus and the minus basis. And then you just correct your errors according to what you measured on M1 and M2. So in this case, you just put a Z gate on the first qubit and you fix your error. So from these two examples, you can kind of see that sometimes if you have a certain error, most often that error will correct the original error by itself. So this will be kind of true when we go into other error correction schemes as well. So then the very first qubit code basically is coming from Shaw. He uses 9 qubit code. Basically, it is a combination of bit flip and the phase flip codes. So you can see that this is the qubit that you want to encode, and then you prepare 9 qubits, and the first part will be your phase flip, and then the second part will be your individual bit flip. So then you can try to see what kind of qubits that this show code will be encoded into. So you just write down everything, and then the first part is basically the tensor product, and then the second step here, you just change your 1, 3, and 7 qubit to plus, and then minus. Then from here, we see that what is this? So this is a third step. So this basically means this. And then the minus 0, 0 basically means this. So we kind of look at the bit flip code and what does it does. This individual part basically flips to 111, 000 plus 111. And then this flips to 000 minus 111. So together with this, because you have 3 parts, so that's why you have 1 over 2 square root of 2. And your Shaw encoded qubit is something like this. So this means that you tensor product this part 3 times. As for the example for error correction part, I didn't do it because, I mean, obviously you can see that this is kind of complex. So I will just leave it at that at the moment. So I think this is my last slide.
Choong,
Yeah.
sorry, I don't know a lot of, there are a lot of new terms. Just curious, in the pictures now, what is the meaning of the red line? Is there any meaning?
The
Or
the red
just,
line, I just want to show that at this point, what is your quantum state? At
oh,
this point, what
okay.
is your quantum state? And at this point, what is your quantum state? So a lot of the times, especially because we are not exactly like the experts in quantum info, so I think it'll be useful to analyze step by step what this kind of circuit does. Like, for example, once we understand what this kind of C naught gates does, then you can see that all the structure actually copies one another. So that's the point of the read lines.
All right, thank you.
Is there any questions or maybe comments? If not, then maybe we can end the recording.
Wait. And the recording, okay.